Welcome back. This would be the first of a series of lectures on porous electrode modeling. So this would be the introduction wherein we give the motivation and the scope. Um, it is a very important topic, especially practiced by electrochemical engineers in the context of batteries and so on. So let us get started. So why do we need this? First, in our previous lectures on electrochemical thermodynamics, electrochemical kinetics, and electrochemical transport phenomena, we addressed all these issues with minimal inclusion of structural complexity. What do we mean by that? We had taken just a flat surface. This is the electrode surface. So the electrolyte and electrode interface was structurally simple. In this case, it was flat. So this was good enough to elaborate the thermodynamics, kinetics, and transport phenomena. But the real electrodes are not like that. They are fairly structurally complex and they are porous. So if you want to look at this structure, you have to look at it from the point of the entire electrochemical system. So this structure goes into an electrode like this, okay? So it is not a monolith, but a porous structure which has solid, liquid, and in some cases, gases also. So this is a monolith kind of structure, but uh, which never occurs in reality. So the real structures are fairly porous. So what are the reason first we need that is all the action in an electrochemical device is at the interface. So you want to maximize the surface area of the interface. So the interfacial area has to be maximized. So we typically use a porous uh, solid so that the ratio of surface area to overall volume is greater. This introduces complexities. First, the complexity is there should be a continuous pathway. Okay, so the transport should not be hindered enormously by the porosity. So transport is a main challenge. For example, if you have metallic network, there should be a continuous pathway for the electron to transfer from the surface of the electrode electrolyte interface all the way to the current collector. That is, from here to this point, okay, if the current is being collected from this surface, the transport of electrons should be possible. Likewise, we should not be transport limited within the electrode. So transport is a big aspect. In addition, there are other complexities. Often we need what we refer to as three-phase boundaries. What do we mean by that? Supposing we have a fuel cell. The fuel cell H2 may come in, okay, and then they may dissociate to form, let's say, proton, which goes into a liquid, and the electron goes into a solid. So the active sites are the sites wherein all the three phases, the gas phase, the liquid phase, and the solid come together. These points or surfaces are called three-phase boundary. In fact, it is a boundary, okay? So if you imagine looking at this structure from the top, the this perimeter will be the boundary for all the three phases to come together. So what are we emphasizing here? We need porous electrode in order to have large surface area to maximize the electrolyte interface. You need large storage volume. So here, this material, um, this is a solid material that is being stored in this electrode, and we need significant storage volume but still this should be accessible to the electrolyte and so on. So we need significant transport, facile transport of all the relevant species. It can be an ionic species, it can be a gas that is being transported, or it can be electrons that are getting transported. We need facile transport. We need three-phase boundary, which is where much of the electrochemical action is. And this continuous pathway, which we talked about, especially for electrons, that is required. These pathways are called percolation pathways. Okay, so there is a continuous transport um, pathway between, let's say, the current collector and the electrode electrolyte interface. Such pathways are called percolation pathways. So this provides a motivation for modeling porous structures. The entire field of porous structure modeling is very elegant exercise in modeling per se. This was practiced for many decades by John Newman at UC Berkeley in the context of battery modeling and so on. And many of his students um, have taken up, and this is a very deep area of electrochemical engineering research literature. So it also tells you how to approach a complex problem. So we, in this series of lectures, we will introduce minimal, I mean, instead of having a flat surface, we would introduce a porous structure, but the complexity introduced will also be in a way minimal. Okay, so we would be looking at narrow cylindrical pores. Okay, so to instead of looking at a complex three-dimensional random network, we would minimize the structural complexity so that the essence of the problem is still represented, but still we can handle this problem mathematically. Remember, we are thinking about transport of three kinds of quantities. One is electronic pathway at the solid, then there are gas transport, and also liquid percolation pathways are also involved. So we will start looking at the mathematical description of the porous electrode in the next lecture. Thank you.